of the things about stars is that they are underappreciated in a sense that, like, my friends at the observatory, you know, who wants to look at a star through a telescope when you can look at Jupiter through a telescope, right? But stars can be very pretty through the telescope. So if you ever make it out there, say, I want to look at a red star, I want to look at a blue star, I want to look at a green star, heaven forbid, I don't know. Greens probably look kind of like blues or whites. But stars that come in different flavors, you can almost see that by just the color. And the color is an indication of the chemistry that's going on with regard to that star. So in the video, you're going to see that low mass stars, less massive stars, are going to be kind of your long living stars, and they're red. The more massive stars, depending upon what stage of their life they're in, if they're kind of in their, what we call the main sequence, their prime of time, they're going to be a kind of a blue color, and they are going to end their lives explosively. So one of the things about stars, and this is where I'm going to hand out, today's April 2nd, yay! This is a sky map for the middle of April. So, where you get these is on the bottom. It's called skymaps.com, so these are free. And, hey, Ian, so you can see that they, right off the bat, the dots are the stars, obviously, and you can see some constellations drawn in. But you see that the stars have different, the stars have different sizes. So in the lower right-hand corner, you can kind of see what that, and it pertains to this slide, what those sizes mean. I can't remember. So do you write that for me? That's right there. Okay. So here's 4 and 5. I'm not 5. So 4 is really short. But the thing you notice, not only the color, but stars are different brightnesses. That's my point. So clear back in the BCs, I think of this guy, Hipparchus, laying on his back and looking up at the stars. And for whatever reason, he said, the brightest star I can see, I'm going to call a +1. And the dimmest star I can see, I'm going to call it a +6. And you're like, oh, really? So anyway, that's kind of where we are. So we adopted that same scale. So if you look at the sheet I gave you with the constellations, you can see this is the same scale. So magnitude -1. Yeah, there is stuff -1. And then I kind of scratch my head like, so he didn't see these bright, I'm not sure how that works. Okay. The other thing about the scale, the brightness scale, is it's a log base 10. So if you skip from a 1 to a 2, that's our factor of 10, getting dimmer, +2. Okay, so you can have negative brightnesses, and they're very bright. So that's kind of how that works. The other thing while I'm thinking about it is if you flip this over, this is kind of fun, because you can see kind of on the right there, broad categories of objects that you might enjoy. There are a lot of objects you can enjoy just with your naked eye, with binoculars, and then the last one is with a telescope. So it's kind of fun. And I flip it over one more time. I like this sky map for a lot of different reasons. And then, so over here on the left, it says that, what's going on with regard to this month, things that might be kind of fun to look at. And I couldn't believe that and somebody pointed out to me the whole blue moon thing. So I sent everybody a link about the blue moon that we experienced on Saturday. So Saturday was the last day of March. And it just so happened then that we had a full moon at the end of March and a full moon at the beginning of March. So that made that second one a blue moon. That's it. Okay. So, like once a blue moon. So, and the same phenomenon happened, what had it been? In February? January? I don't know. But it's kind of rare to have those close together. So with regard to how bright a star is, so the smaller or more negative a number, the brighter it is. So I've got some kind of numbers here for you guys to fill in. Check this out. So the more negative is, the brighter it is. The sun is a -26.7. right? Full moon, negative 12.6. And these are all kind of missing. And they are kind of small, fill in there, I know. Negative 12.6. Actually, at the observatory, we get a lot of traffic. It feels like during full moon, you're like, you can come, but the only thing we can see is the moon because it washes out everything else. So, Venus, relatively bright. You're talking a negative 4.4. And when we briefly covered Venus, remember Venus is the one that has those clouds that are not made of water, but they're made of sulfuric acid. Venus was in the news recently that scientists are looking at those clouds, the Venusian clouds, the clouds on Venus, and they're thinking that could actually, they could have life there. And I thought, oh, really? That's so cool. Anyway. The Sirius is actually up these days, I think. Sirius is part of the constellation, is not here, Canis Major, and it's the dog, it's Orion's dog. So we can kind of see Orion, it's getting lower and lower, it's going to be kind of it's right now it's on the west. So things on the west, you figure, if this is about 9 p.m. or so, in the middle of the month, things in the west, just like the sun sets, things as in stars on the west actually set. So actually you can see Sirius right there. And it's the part of Canis Major, which is the big dog. Now we get kind of dim. Naked eye limit, again, kind of like Hipparchus came up with. You're looking at a plus 6.0. Everybody's eyes are a little different, and viewing conditions make a big difference. If you put binoculars to your eyes, then you are actually gathering that light, and you can see objects as dim as a plus 10. Pluto, a plus 15, plus 15.1. And if you use a large telescope on Earth, or heaven forbid, you get access to the Hubble Space Telescope, where you look at some of those pictures. Hubble Space Telescope is actually orbiting the Earth, and it's going pole to pole, not around the equator, pole to pole, every hour and a half or so. You can see objects as dim as plus 30. Plus 30. So the higher the number, the dimmer the object. So sometimes some people like to chase, they call chasing satellites, and actually a new satellite system is going up which won't be as nearly as reflective as the old satellite system in general. But a satellite, if this is the main body of the satellite, it has like, I always call them kind of arms like this. These are solar panels that help the satellite do its business. And so if the angle of, this is the Earth, here's the satellite, there's the sun. If all of that lines up, you could actually catch a glint of the satellite. And it looks like a streak. It'll just kind of get bright and then dim. Okay, so that's the satellite flaring. It's not really flaring, but from our perspective, the sunlight is hitting it just right. So my point is that they talk about those flares and they give them magnitude numbers. So we get really excited if it's a negative number, because it's bright. Well, okay. Now there's a lot of things in science you're like, really? Did you have to do it that way? So what we were just talking about is brightness, or what we call apparent, or what it appears magnitude. Let's see what it calls down here. Yeah, just star magnitude, lowercase m. Now, scientists then need to actually be able to talk about stars, what their real brightness is, removing what we say the effective distance. And that is actually what we call absolute brightness. Oops, I see I hit a word here, source. This might or might not look familiar, and everybody knows. Like if a car gets farther from you, its lights are going to be dimmer, not so bright in your eyes. That's it. And the way it works is the farther it gets from you, it has to, those car lights will go in all directions. And so it's a dilution of what we call the inverse square law. So for every unit it goes away, it gets dimmer by a factor of that distance raised to the second power. So anyway, we have this other scale of brightness, and it's called absolute. The word is absolute there. absolute magnitude. And you're like, really, could you not come up with, because apparent magnitude or brightness, we talked about a minute ago. I mean, that's what we all care about, how bright something appears. But we need to be able to kind of compare stars as if they were all on the same level playing field. So what we do now, we can't relocate stars, but we kind of pretend like we relocate stars. We talked about a light year the other day, and if you take like 3.26 light years, you get a PC, which is a parsec. So anyway, so if this is the Earth, we kind of do the math and we place the stars as if they are 10 parsecs from us, and then look how bright they are. And that's their absolute magnitude. Okay, that's it. So we kind of normalize them for distance. So the sun, we said its apparent magnitude is negative 26.7. Well, dang, I mean, it's like 1 AU. It's pretty darn close. So if we were to put it 10 parsecs away, which is about, so it must be about 30 light years or so? About 30 light years. Then actually it would look like a plus 4.9. See how that works? It makes sense. It would be dimmer. It would appear dimmer. So we use a capital M for absolute magnitude. So its absolute magnitude must be plus 4.9. It's so special to us. Negative 26.7, but our sun is actually a really average star. Okay. So the word here is compare. Absolute magnitude is going to be important here in a minute to kind of compare apples to apples or stars to stars. Removing the effective distance to see kind of really how much energy they're putting out if they were all on the same playing field. So you're like, I feel like we've come full circle a little bit, but we still have weather and earth science to talk about. But the electromagnetic radiation, remember we said that that visible light is only one cousin or one form of electromagnetic radiation. So this kind of goes back to, if I were to ask you just generally, red or blue, cool stars are what color? Red or blue? They are red. Cool stars are red. Hot stars are blue. Yeah, exactly. And actually that kind of, yeah, it is opposite. I've heard us do that. Red hot, you know, like, oh, it's red. No, it's red cool, blue or white hot. Blue, white hot. So. And that's kind of consistent with this idea of, remember we said this over here is more energetic, clear back in our first unit, and this over here is least energetic. There on the right, it's less energetic. There on the left, it's more energetic. So you kind of have your blue stars there, more energetic, your red stars here, less energetic. So according to Wien's law, that peaked, if you were to take, I'm going to kind of show you, in a minute. This right here, see these kind of curves? Okay, we have a blue curve, a yellow curve, and a red curve. Those curves are so cool because, no pun intended, but they are actually representing like a signature of what a star is sending us. So basically for the red one, that star is sending us, and this is energies. This is electromagnetic radiation energies along the x-axis. It's sending this much, this wavelength, this much, this wavelength, this much, this wavelength, etc. It's what we call a black body radiation curve. Another star here, another star here. Now, if you were just to eyeball those two things, one of the things is you can see the blue star, which you guys said is hotter. Okay, the peak is slanted over here. The peak is over here, okay? And also it's higher. So it's more intense and it's gonna have kind of a blue color. They're hotter stars. The blue stars are hotter than the red stars. These are black body radiation curves. And then my favorite little, see here's a human, like a black body radiation curve of human. You know, our peak's a lot lower and we're much way over here to just the infrared. Okay. Speaking of fingerprints, I have absorption and emission lines. Like, oh man, and I can't remember if we talked about this in our physics unit or probably our chemistry unit. I think you had a test on your chemistry test question on your chemistry test that said what part of the atom makes spectral lines like this, and you told me, is it proton, neutron, electron? Which one can jump energy-wise? Electron. Electrons are making this. Yep, exactly. So astronomers years ago actually got these sort of kind of fingerprints from stars, okay? And those fingerprints, those dark lines, those what we call spectral lines, okay, kind of looks like a DNA thing almost. Those spectral lines actually, if you know what you're looking for or looking at, are an indication of what elements are associated with that star. Is that not cool or what? So you get a sense for temperature. You can kind of see temperature here along the side. 3000 K stands for what? What's temperature that we K? Kelvin. 3000 Kelvin. 3000 Kelvin up here to 30,000 Kelvin. You see all sorts of kind of elements: hydrogen, helium, carbon, iron, oxygen, titanium. So this one right here, it goes O, B, A, F, G, K, M. O, B, A, F, G, K, M. And those, by the way, those letters are over here on the side of these different types of stars. O, B, A, F, G, K, M. Here they are. Those are the different types of stars. I mentioned our sun is kind of an average star. Our sun is a G-type star. Right there. That's the fingerprint of our star, of our sun. And a good way to remember this is O, be a fine guy or girl, kiss me. Students all across the United States are learning that little mnemonic device, where O is the hottest and M is the coolest. Okay. So, we've kind of talked about a few things about stars. Now, in math and science, because I heard math was like calculus, was like invented by two people about the same time. I don't know if that's true or not. Was it Laplace or something and Newton? I don't know, something. And along those lines, these two scientists, Hertzsprung and Russell, they were on two different continents and came up with the same idea at the same time. Now, a lot of things, what we do in science is we gather data and then we kind of look at it. One of the ways we can look at it is by preparing what we call a scatter plot. So this is a scatter plot. The word is patterns. This is a scatter plot. And it may or may not show anything. Now, actually I worked for a scientist for about a year who was researching coal. And he would just grab 2 or maybe 3 criteria and he'd look to see if they correlate, if there was any connection. So the 2 things that Hertzsprung and Russell looked at, one is the surface temperature, we're going to plot that along the x-axis, and the other is luminosity. But this isn't just any luminosity. See if I can find my pen. This luminosity is absolute brightness, not the apparent brightness, absolute brightness. That's what luminosity basically is. Luminosity is how much energy it's pumping out, but absolute brightness is kind of on a level playing field how bright everything is over here. Absolute magnitude, I said brightness, sorry. Absolute magnitude over here, and that corresponds with luminosity. And then we have temperature. Now, let's get our bearings though before we kind of finish up talking about this HR diagram, Hertzsprung-Russell diagram. Check out the temperature. Drat. It's kind of, I'm not sure why they did this, honestly. Which side is a hotter side? The left or the right along the x-axis? Yeah, the left is hotter. So we have hot stars over here, cool stars over here. Now I do like the way I think this came from your textbook, your author's done. Can you see if you look at the top there? You see your 7 spectral types. The O, be a fine guy or girl, kiss me, corresponds to these surface temperatures. Now, they probably, when they first did it, just put dots, but you can see what your author's done is try to kind of give some life to the particular star they were putting on the scatter plot. So you can see these all represent stars, and they already kind of showed you that the hotter, more luminous stars up here anyway are bigger, and they really are bigger. These guys down here, smaller. Lower mass, okay. So one of the things we're going to see in the video too is we can kind of, on this scatter plot, get a sense for 3, if not 4 different groups. So one of the groups is the main sequence. Let's see. Clusters is the word there, clusters. Here's the main sequence right here that I'm circling. Okay. And main sequence is like where stars spend most of their lives. But we said more massive stars live their lives more quickly. Then we have giants. I just call them giants, but we've got giants here and we've got supergiants. And then down here we've got white dwarfs. Kind of in the order I showed you is kind of the order that stars kind of change their stages. And as they change their stages, they're going to be at different places on this HR diagram, Hirschsprung-Russell diagram. Okay, blue, red, blue and red. So for the main sequence stage, the blue stars are the most massive and the red stars are the least massive. All right, so again, we won't see the whole thing. Let's see, we only have, so 25 minutes, that's about what I was hoping for, 25 minutes to kind of see this. And it'll talk about the different, the way a star comes alive and lives its life, and starting kind of how a star dies, which is kind of depressing.